Good morning, everyone. My name is Judith Narayan, and currently I am pursuing my MTech in Artificial Intelligence from Indian Institute of Technology, Patna. So, today I am going to discuss some interesting topics in the field of artificial intelligence. So, my topic is pruning in multiplayer game. So, I am going to discuss this topic under the guidance of Dr. Arjit Mandal and collaboration with my team member uh, Ansu Kumari and Anu Kumari. So, in this discussion, I'm going to cover introduction part and multiplayer games part and Maxn algorithm, and rest part will be covered by my team members. So let's start. So, artificial intelligence in game playing has been a long-standing challenge. So I think in 1997, first time a company named uh, Deep Blue, that's the part of IBM, the first company that defeated the World Chess Championship. Uh, After that, many research is happening in this field. So scientists and AI researchers and the computer science researchers mainly focus on two-player games using well-established techniques such as Minimax and Alpha-Beta Pruning. So, however, a multiplayer games introduce additional complexities. So, as we know that when we increase the number of players, the game complexity will be increased. So, in multiplayer games, it involves multiple independent decision makers. So, that's why for multiplayer games, uh, the two-player games algorithm don't work properly. So, for multiplayer games, we require advanced algorithm like Maxn algorithm to solve the complexity problem. So, so let's discuss the multiplayer games. So, multiplayer games, as we know that it's more than two players. In two-player games, we use the Minimax and Alpha-Beta Pruning. It works well for the two-player games, but not for the multiplayer games. So we use Maxwell algorithm for multiplayer games. So let's Maxwell algorithm. Yeah, it's developed in 1986 to handle multiplayer games by Irani and Lakharat. So Maxwell algorithm is a generalization of Minimax for multiplayer games. So in two-player games, the Minimax algorithm is commonly used, where one player try to maximize their scores and other try to minimize it. However, in multiplayer games, for example, three players, there is no opponent. So each player is playing for themselves. The Maxwell algorithm ensures that each player maximize their own scores. So let me discuss this tree. So uh, in multiplayer game, so let it's player one, player two, player three, player one, player two, player three, and so on. So in multiplayer game, every player is independent of each others. So each player uh, wants to maximize their scores. So play in player one, a score is seven. Player two, its a score is three, and player three, its a score is zero. So here, player two wants to maximize their scores. In both, where we have to look the score of player two. So the left part, the player two has more scores. So we will carry forward to here. So 7-3, 0 will be the score score in player 2 will be maximized. Similarly, we look for the player 2, so we carry forward the uh, maximum scores. Similarly, in this case also. So after this, player 1 will look for the maximum value. So just look all the scores uh, of player 1. Uh, Left part, that's its maximum score for player 1. So it's carry forward for the next, and 730 will be the max score. So let me discuss through the algorithm by coding.
Hello everyone, I am Anshu Kumari, and in this section we will learn about pruning techniques. As in the previous section, we already discussed what is Maxn algorithm and how it is used in multiplayer games. Now, what is pruning techniques and how it is useful for us? Pruning techniques help us to reduce the unnecessary branches which do not lead to optimal solution. Also, it helps in making decision faster. Now let's discuss some of the pruning technique, their limitation and advantage. So first pruning technique we will discuss is immediate pruning. Here we will look for maximum possible value. That is when a player scored maximum possible value, we will prune all other siblings from there. Now let's take an example of this three-player game tree and understand how we do immediate pruning. Here max sum indicate that the total sum of all players should equal to 10 and max p indicate that the total sum of total possible score of a player should equal to 10. Now at node A, when we look at node A, we are getting 0 10 0 from left child, which says that player 2 has scored 10. And also we know that for every player we have maximum 10 values which player 2 has already acquired, so there is no need of looking further and we can prune this node from the here. So this kind of pruning is known as immediate pruning, but the immediate pruning has a disadvantage that it will always work when we have maximum possible score, that is max p. Now let us look on another pruning technique, that is shallow pruning. In shallow pruning, we look at information from parent node which we use to prune the branches at child level. Here we declare two kind of bound, an upper bound and a lower bound. The upper bound is declared on the total sum as we seen in previous example, max sum is equal to 10, and the lower bound is declared on individual player score. For example, the score of a player should be greater than 0. Now let's take an example and understand how shallow pruning works. Here at node A will get 631 from left node, which says that player 1 has already acquired score 6 and we are looking for greater value, that is player 1 score should always greater than or equal to 6, which indirectly says that for player 2 and player 3 we have remained with value which is smaller than 4 or equal to 4. Similarly here we get for player 1 we are getting smaller than equal to 5 as player 2 has already achieved 5 score. As we know we already got 6 score for player 1, so we will never go toward that branch which leads to smaller values for player 1. Hence there is no need of exploring further and we can prune all the branches available here. This kind of pruning is known as shallow pruning. The shallow pruning has also disadvantage that it will work when we have constant sum game, means when we have a maximum sum possible sum of all scores should constant throughout the game. And also there is a rule which need to be followed to perform shallow pruning, that is max sum should always greater than 2 times of max p. Now let us discuss another pruning technique, that is deep pruning. In deep pruning, we take an information from ancestor node, we can say grandparent node, and based on that information we prune further. It was well in two player game, but let's see how it is working in multiplayer game. Now if we look at node C, here we got 5 score for player 3, which says that for player 1 we rest with the value smaller than 5 or equal to 5. Sorry, it should be smaller than here, but we have already acquired 6 at node A for player 1, so we will there is no meaning of going further and exploring this branch, so we can prune this branch, and this type of pruning is known as deep pruning. But let's say for a time being we are not pruning this one, so this value will go here 226, and at node E the player 2 will try to maximize its score, so we'll choose 730 here, which ultimately cause score for player 1 is 7, which is greater than 7. Hence we are getting maximum value without pruning, which we are not getting while doing deep pruning. So we can conclude that deep pruning is not work well in multiplayer game. So now let's discuss another approach toward it. We can reduce our multiplayer game to paranoid two player game. Here we assume that all opponents are working together against the main player. The main player we say that as max player, and all other player which are working together to minimize the value of max player are called main player. Here the max player has branching factor B, so remaining main players have branching factor B to the power n minus 1. The reduction of paranoid two-player game has also some limitation. It is unrealistic to assume that all the opponents are working together against the main player, and also it do not lead to it leads to suboptimal solutions. The next pruning techniques we are going to discuss is based on heuristic function, which is used to estimate upper and lower bound. The heuristic must be monotonic in nature, and the heuristic guaranteed always a move is better for a time being. Here we can see that given heuristic for 1 should is smaller than 5 means the score for player 1 should always be smaller than equal to 5. Similarly here heuristic for 2 is smaller than 5, which means that for player 2 we will always get score smaller than or equal to 9. Now we have achieved 790 here. For player 2 we have achieved 9 score, and we cannot get greater values than the 9, so we can prune all other branches available here, because we have already achieved the maximum possible value for player 2. So this kind of pruning technique is known as branch bound pruning. This has also some limitation as we have seen in the deep pruning, but there is also some pruning techniques available which overcome the limitation of branch and bound, which will be discussed by my friend Anukumari, and I will stop here. Thank you.
I am Mannu Kumari. I am presenting this slide. This slide describes the hybrid approach of alpha-beta branch and bound pruning, which enhance the decision-making efficiency for the tree game search algorithm. Basically, we have earlier seen that shallow pruning techniques, which is based on the backup value, which means that it eliminates the branch early based on the value already computed from the previous node, and branch and bound pruning techniques, which means that heuristic bounds to refine the search algorithm. This both combined together gives significant reduction of the number of nodes evaluated and leading to the better computational efficiency. In the next slide, we have implemented the method which improve the search strategy and pruning techniques to enhance the upper bound calculation. This is the equation a maximum minus score j minus summation of h of x, that is for x is not equals to I and j. Here maximum denotes the maximum possible score for the player, and score j denotes that the current score for the player j, and summation of h of x denotes that the heuristic estimates for the other player. This equation tightens the upper bound by subtracting the heuristic estimates for remaining players. By doing this, we have making pruning more aggressive and reducing the unnecessary evaluation and making the optimization to the decision making. In this slide, we have mentioned the graph for the alpha beta branch and bound pruning. Here, each square node denotes that the game state, and the number in this parenthesis represents that the evaluation value for the different players. Initially, node 1 has the upper bound, which means that the first player has the minimum of the bound 6, and the player third and the second has the upper bound of 4. And this is the shallow pruning bounds, which is a subtree, and alpha beta branch and bound, which restrict the search. Node right child of node A has the estimate heuristic h of 3 is greater than equals to 2, which means that if it is not evaluate its existing bound, its branch gets pruned. This is the experimental result. This experiment tested on the different pruning techniques on the Sergeant Major 3-player card games over 200 random trays for the better efficiency. Compared with the pruning methods like shallow pruning, which prunes the branch early but it's not prune aggressive. Branch and bound, it uses the heuristic for the pruning but it is not optimal. Alpha beta branch and bound, which is a combination of shallow pruning and branch and bound, which makes efficient better decision making. Paranoid 2-player reduction, it is a multiplayer game which reduced in 2-player game, assuming that the other player are in one group. We have results that the average node expanded for the full tree without pruning. We have 3.33 billions of nodes. By applying branch and bound pruning approach, we have 32.7 million of node, and similarly shallow pruning applying, we have 26.8 millions of node, and for alpha beta branch and bound we have 1.43 million, and similarly for the paranoids 437.6 k of nodes, and paranoid with heuristic we have 36k. This is the best. We are concluding that the alpha beta branch and bound reduce the number of nodes expansion, making it more efficient than the shallow pruning techniques and the branch and bound techniques. However, alpha beta branch and bound is still not efficient as compared to the paranoid 2-player game. Bound is still challenging for the multiplayer game compared to the 2-player game. Thank you.